Greetings, everybody. This is Atlas Training session number 4. Let's take a look and see. Emil and Annegret, I see you're here. Welcome. Let's turn on the questions. Questions. How do I see the questions? Oh, here we go. Question and answers. Okay. Hi, Jeff. Hope you had a good Easter weekend. Thank you, Emil. I did. All right, so I'll get started. So what we're going to talk about today is more about parameters, and I'm going to give everything in between the discrete series and the principal series, and give some examples and how to understand parameters. And then I thought I'd go on and talk about composition series and character formulas and the Kazhdan-Lusztig polynomials. So let's get started. So I thought I'd start by looking at the slides from last time and just recalling where we were about parameters. So remember, a parameter is a triple x, lambda, and nu. And excuse me, go to the right page here. Sorry, take me a second to get straightened out. Okay, and so x is an element of KGB, and attached to x is this Cartan involution theta x of H. And lambda is an element of this lattice x upper star shifted by rho modulo something. And nu is an element of this rational, this lattice tensor over Q modulo something. And you can identify that with just this x upper star tensored Q, the fixed points of minus theta x. So that's the triple x, lambda, and nu. And I'll remind you that when you have a triple like that, the infinitesimal character is given by this expression. And notice that 1 plus theta x over 2 times lambda is well defined on this quotient where lambda lives. And similarly for nu. And let me go back before I get to this page. Okay, so that's just a reminder what parameters are. And now I'm going to talk a little bit more about parameters and what they mean. And so the main point is there's a notion of equivalence of parameters, and I'm not going to give it here. There's a reference, this paper on the Atlas website gives the details of what this equivalence of parameters is. There's some easy parts of it, and then there's some harder parts. And anyway, I'm not going to get into the details of that right here. But the point of this definition is the following theorem. There are canonical bijections. I see my phone is ringing, but I'm going to ignore it. Canonical bijections, parameters for G, and standard modules for G, and irreducible representations of G. And the definition of equivalence was more or less chosen to make this theorem come out to be true. And the bijections are given as follows. From 1 to 2, if you give me a parameter P, attached to it is a parameter which I usually call I of P, and I is short for induced. And this I of P is a full induced from P up to G. P is a cuspidal parabolic, a real parabolic, and sigma is a discrete series of the Levy factor or a limit thereof. And this is a so-called standard module. It's a full induced. The bijection from 2 to 3 is that the way this is set up, the conditions on P are that this induced representation always has a unique irreducible quotient, always. And so that irreducible quotient is denoted J, and the bijection from 2 to 3 is given by taking the irreducible quotient of the standard module. And so when you compose those, you get the bijection from 1 to 3. If you give me a parameter P, attached to it is an irreducible representation denoted J of P, which is the unique irreducible quotient of I of P. Okay. So let's see. Okay, welcome Monagret and Susanna and Emil. We're welcome. And so this is the sort of heart of the business about parameters in Atlas is this bijection between these three sets. And we've seen a bunch of examples of this, and I'm going to do some more today. Let's see, did I have anything else on these slides? Oh yeah, so I'm going to talk about if you have a standard module, that's a full induced, it could be reducible. And so one can talk about the composition series of the standard module. And conversely, inversely perhaps, is the notion of the character formula, which is to say, if you have an irreducible representation, according to the Kazhdan-Listic theory, you can write it as a formal linear combination of standard modules. That's called the character formula of J of P. And both of these things, the composition series and the character formula, are given by the Kazhdan-Listic polynomials. So that's what I'm going to talk about. Questions before I begin? Let me pause there. All righty. So let's kill this window here and go back to the, not go back to me, but just momentarily, now go back to the software, which is where, maybe here. Nope, that's not the right place. Let's try that again. Where do I have the software running? Maybe here? Nope, that's not it either. Excuse me. I guess I don't have the software running. Let's run it. Good. All right, one more try. There we go. That should do it. All right, so let me bring this where I can see it better. All right, and okay. Oh, I forgot to mention, I had a picture of the website up when I started, and I meant to mention that there's a new collection of AT files there. I think it's 0.6.3, which I recommend you download. And when you get around to it, well, I should say when I get around to it, there's, excuse me, there have been some substantial under the hood changes to the software by Mark. And as a result, the core software has been changed, and you should get that. If you want, if you're a Git user, you can get it using Git from the master branch. If you want to wait, I'll be posting an update on the website in the next couple of days. For most people, it will be invisible. You won't notice the difference. So there's no hurry on that. Although the AT files I do recommend you get because there's some new things in there. All righty. So let's see. Let's launch the software. Excuse me. Let's launch the software. All right. And I changed the all file so that it really loads almost everything now. And so I'm just going to load all. And let's just refresh our memory how all of this works and start by doing a couple examples of parameters. So let's set G is equal to, of course, what else but SL2R. And let's set P to be the trivial representation of G. And there it is, excuse me. And so remember, we can take X is the x from this fellow, and we can look at the involution of x and see that it's -1, which is to say this is the underlying Cartan is split. And this is a principal series representation. The infinitesimal character of it, of course, is 1, which is rho of G. And so that's the principal series. And last time we talked about discrete series. So for example, I can look at the discrete series of G. I forget the syntax here, so I'm going to remind myself what type of discrete series. You give it a KGB element and a rational vector. So for example, let's say Q is the discrete series for KGB element 0 at rho. There's Q. Okay, so the main thing I want to talk about today, well, I want to get started by talking about is general parameters, not necessarily discrete series or minimal principal series. So let's start slowly. So we're on SL2. I have a discrete series of SL2. What about the other discrete series of SL2? Well, let's see. So one helpful thing is to look at the block of the trivial representation. And remember, it has 3 representations in it, 2 discrete series and the principal series. I've already got one of the discrete series. That's the one with KGB element 0. And the other one would be, let's see, so I set Q to be the discrete series. Let's set R to be the discrete series with KGB element 1, for example. And I'll remind you that it's often helpful to fix a base point x, and so in this case I'm going to take KGB element 0, and then I can look at the Harish-Chandra parameter of Q with respect to x. Oops, not interesting. Q with this is sorry, x sub b is what I wanted. That's better. The Harish-Chandra parameter of Q is 1, and the Harish-Chandra parameter of this other discrete series is -1. So that's the holomorphic and the anti-holomorphic discrete series, respectively. All right, let me pause there. Are there any questions? All right, so let's do one other small example before we move on to a bigger group. I know I've done this one before, but it's worth repeating. Let's redefine G to be PGL2R. This is very similar to SL2R, but it's different in important and interesting ways. Let's redefine P to be the trivial of PGL2. And let's print the block of P. And now, as we've seen this before, this block has one principal series number 0 and one discrete series number 0 and 2 principal series numbered 1 and 2. By the way, somebody, I forget, Brian or somebody said that when I used the cursor on the screen, it didn't seem to line up with what I was talking about. I'm not sure what that's about, but I'll try and avoid that problem. So let's see. So why is there only one discrete series here? So let's see. Let's set. Let's take Q to be the discrete series of KGB G0 at rho of G. What is Q? There it is. Incidentally, rho of G in these coordinates is 1/2. Something to keep in mind. And the fact, by the way, that that's not an integer is to say that when you're talking about the group PGL2, this x upper star plus rho, it really matters. You're not in x upper star any longer. X upper star plus rho is the half integers. In any event, that's the discrete series. And what's its Harshchandra parameter of Q? It's 1/2. And there's only one discrete series here. Let's look at KGB of G. There's only one KGB element to use, and that is to say there's only one discrete series. Equivalently, the simple reflection S alpha is in the Wahl group of K. K is disconnected in this case. So, on the other hand, there are two principal series in this block. These two guys right here. And they both have infinitesimal character rho, but they differ on the disconnectedness. Now, interestingly, SL2, maybe I should illustrate one last thing before I move on. So P is the trivial parameter for this group. And there's this command, all parameters, I think P is the command. Oops, not an integer vector, isn't that interesting? Not sure what that's about. Not an integer vector. So it's complaining something about rho not being an integer. Came back to bite me there, I think. I'm not sure. In any event, this isn't so important. The only point I wanted to make is that let's look at this block again. Print block of the trivial of G. I mentioned that it has these two principal series in it, and print block sizes, or just block sizes, I think it is, of G. You see that this group, which is on the second row here, has 4 representations with infinitesimal character rho. 3 of them are the ones we're looking at here. And I'm sorry, I misspoke. These 3 are at infinitesimal character rho, and there's one other at a different infinitesimal character. All right. Anyway, this is. Let's look at let's go on to SP4 and look at some more representations. So let's say G is equal to SP4R, and let's set B to be the block of the trivial of G, and let's print the block of the trivial of G. All right. So there are 12 representations in the block of the trivial representation. And so far, the ones that we understand reasonably well are these 4 being the discrete series of SP4. And you can tell that they're discrete series in various ways. The simplest is to note that all of the roots are imaginary. And another thing is that their lengths are all 0. At the other end are these 2 principal series. These are where x is equal to 10, as you see. Whoops. X is equal to 10 here, and all of the roots are real.
And so the main thing I'd like to do now is see how do we understand everything in between. Whoops, not number 3, but 4 through 9. Okay, so let's start by looking at representation number 4. Let's take P to be representation number 4 with x is equal to 5. Okay, so what do I know about this representation? Well, of course, its infinitesimal character is rho, and nu. Well, let's take x to be x of this fellow, and let's look at the involution of x. So this is neither 1 nor -1. This is one of the intermediate cartons, and this is what people sometimes call the SL2 carton or the long root carton. The Levy factor here is SL2 cross GL1. Now, how did I know that? Well, I'll come back to that. Let's see, what did I want to say? So, well, it's worth looking at this involution. Let's give it a name. Theta is this involution, and so in particular, the -1 eigenspace of this involution is the second coordinate. And notice that nu of P indeed lives in the second coordinate. And lambda has to do with the, of course, with the restriction, with this character on the compact carton. So here's what I want to do. So here's a new command, which helps to explain all of this. Let's set P, comma, sigma to be the cuspidal data of P. Okay, so this is an important new command which helps to, well, comes up a lot. So the cuspidal data is the pair, P is a real parabolic, and sigma is a discrete series, or limit, let's just say discrete series of M, which is the Levy factor of P. And then the point is that the corresponding standard module, I of P, is induced, parabolically induced from sigma, from P up to G. Okay, so what is P? Well, P is a little bit strange. It's this pair. It's a sequence of integers in a KGB element. I'm not going to get into the details of this. There are notes on the website about it, but suffice it to say that this is a generalization of a Borel, and the main point is that this 1 is telling you the Levy factor. That 1 is the roots in the Levy factor, and this KGB element is I mean, this has to do with p orbits on G mod B, which is a quotient of B orbits, excuse me, K orbits on G mod P, which is a quotient of K orbits on G mod B. And anyway, I'm not going to go too far down that rabbit hole, except let's set M is the Levy factor of P. And here's where you learn something. M is the disconnected split real group with Lie algebra SL2 GL1. Okay, so what do you know about M? Well, it doesn't really pin down M for you, because either M could be SL2 cross GL1, or it could be GL2. Both of those groups fit this description. But, well, one thing you can do is you can look at the simple roots of M, and you see that the long root 0, 2 is a root of M. And so that identifies this parabolic for you. And in fact, it's SL2 cross GL1. And well, what is this sigma? Sigma is, well, let's see, it's a parameter, but the crucial point is that the sigma is a parameter for M, this subgroup. You can't exactly tell that by looking at it, but it is. And what is it? Well, it's supposed to be a parameter for a discrete series on this Levy factor. And well, the way to think of this Levy factor is this SL2 is the one with the long root 0, 2 in it. And this GL1 is sort of living on the first coordinate, and this nu is on the GL1. And this, this lambda is somehow telling you a discrete series on the Levy factor. Okay, so what's the infinitesimal character of sigma? Well, it's 1, 2, and that's the way induction is set up. It doesn't change the infinitesimal character. It's normalized induction. So when you induce this from P up to G, you're going to get a representation with infinitesimal character 1, 2. And when you're up on G, that's of course conjugate to rho, which is 2, 1. Okay. By the way, what is rho of M while we're at it? We see that rho of M is 0, 1. Okay. So well, let's see, what else can we say about this? Let's look at the Harish-Chandra parameter of sigma. It's 1, 2. Now, I should have mentioned before when I'm talking about discrete series, I always mean, maybe I'll put a little note here, by discrete series, strictly speaking, I mean what's sometimes called relative discrete series, which is to say it's the discrete series modulo the center. So this group that I'm talking about, M, its derived group is SL2, which has discrete series. It has a split torus in the center. So this is strictly speaking a relative discrete series. All right. So that says that this parameter that we're talking about is induced from this Levy factor, and the software knows about induction. So what you can do is you can say induce, I believe, standard. I want to induce the representation sigma from P up to G. Okay. And when I say induce standard, what I mean is this sigma can be viewed either as a standard module or as an irreducible module for the Levy factor, and here I'm viewing it as a standard module. And so when you induce a standard module, you more or less get a standard module, and that's what I'm going to get here. And you see that I get, well, it's 1 times this parameter P, which is what I started with. All right, so before I go on, let me put it in a digression here. So this issue about standard modules versus irreducibles is always an issue. And before I gave this presentation, I started to implement, well, there's something in the software for distinguishing between them, and I'm going to talk about that in a few minutes. Before I started this presentation, I tried to implement standards and irreducibles on the level of for induced representations, and which would clarify this business that I'm talking about here, but I didn't quite get it done in time. So for the moment, it'll take a little bit of explaining, and you'll see in a few minutes when this notion of standard and irreducible module comes in, it'll make things a little bit easier. Okay, so the point is there are two kinds of commands. There's induced standard and there's induced irreducible. And what this means is take view sigma as an irreducible representation of the Levy factor and induce it. And furthermore, write that as a sum of irreducible representations. So when I do that, I get a sum. Okay, so what this means, maybe I should put a little note here for the record. So when I did induce standard, what this means is that induced from P up to G of this discrete series is equal to a single standard module, x is equal to 5, 2, 1, 0, 1. That's what induced standard means. On the other hand, when I do induce irreducible, what that means is that induced from P up to G of this discrete series. Now, in this case, and often, in fact, these discrete series is both a standard or an irreducible module, so you can't. There's not really a distinction there. But the point is, I'm writing this as a sum, sum of irreducible modules for G. Okay. In any event, so what I'm saying here is that this standard module in question with x is equal to 5 is reducible, and it has 3 pieces. Okay, so let's maybe it's worthwhile explaining this business about standards and irreducibles in this example. So I have this parameter P, and as I said in the notes at the beginning, P associated to P is an I of P, which is a standard module, and also J of P, which is an irreducible. And in the old days, and still a lot today, these various commands that we have, the arguments are parameters, and sometimes they're viewed as standards and sometimes they're viewed as irreducibles. And it depends on the context. I'm in the process of implementing a distinction between them, and which will help to clarify that. And so here's the sort of beginning of that. You can say, let's let set irreducible to be J of P. And what this means is P is a parameter. Associated to parameter is an irreducible representation. And that's what this is. And there's a command show to show it. And what it says is it's hardly doing anything here, except that it's putting in this letter J at the beginning here to emphasize that this is an irreducible representation, J, associated to this parameter. The parameter is exactly the one we've been talking about. And the J indicates that we're talking about an irreducible representation here. On the other hand, I can set I, or let's say IND, to be I of P. And if I show this fellow, I see that, this is I standing for a standard module with this given parameter. Okay. And now the advantage of this is that this distinction helps you to know what you're talking about. So, for example, if you have a standard module, you can look at its composition series. Okay, so now back when we were talking about parameters, I would always just say print or print s to look at a parameter. But in the world of what I call modules, where you distinguish between these irreducibles and standards, whenever you want to look at something, you should use this command show. So you take this induced representation, it has a composition series. That composition series is a sum of irreducible representations. And that's what this says. It says that, excuse me, this reducible standard module is the sum 1 times j, 1 times j, 1 times j. It's the sum of these 3 irreducibles with multiplicity 1. And if you go back to my induction, induce irreducible, that's exactly the sum that I had here. So here, when I wrote induce, let me highlight this. When I wrote induce irreducible, I just got a sum of 3 parameters. And well, I know that what this is telling me is a sum of irreducibles because I asked, the command I gave was induce irreducible. And so that must be what this is telling me. But, well, who can remember that? And it often gets confusing. So it's better if you do this show command, and then it actually says, this specifically, I mean, this sum of 3 irreducibles. Okay? And on the flip side, the other direction is when you have when you have an irreducible, you have its character formula. And when you ask for the character formula of an irreducible, that's writing the irreducible as a formal linear combination of full standard modules. And so notice here, these are i's, indicating these are standard modules. And the coefficients have some negative signs. So that's what happens in character formulas. You can have signs. When you have a composition series, they had all better be positive integers, non-negative integers, positive integers. And in a character formula, you're allowed to have pluses and minuses. Okay? So that sort of shows you the 2 pictures of parameters, standards, and irreducibles. And another feature of this syntax is the following. If you ask for the character formula of a standard module, well, what's that going to be? Well, that's probably almost certainly a mistake. You don't usually ask for the character formula of a standard module, and the software will wisely refuse to do it. It will say it's the wrong kind of argument. And similarly, if you ask for the composition series of an irreducible representation, you get an error. So I see here that it actually gives a more helpful error message here. It says composition series is not defined for irreducible modules. And there should be a comparable error message in the case of character formula. So this helps to prevent mistakes. You almost certainly aren't interested in computing the composition series of an irreducible representation. Now, I should say, if you have a standard module, which happens to be irreducible, you can compute its composition series, but that's a different matter. Okay, so that was all about this parameter number 5. So let's look at this block again. Sorry, not number 5, the one with KGB element 5. Okay, so excuse me. This is a representation. It's associated, it's attached to a certain carton. And there are other representations coming from the same carton. And so, for example, I haven't talked too much about this, but there's this, the cross-action. And what that says is that this representation number 4, this column here is telling you about the cross-action. If you do a cross-action in the first simple root, you get representation number 7. And that is to say that that's another representation on the same carton. And you can also do a cross section in 8. And so both of these representations are on this carton. And I believe should be one more. 7, 8, 4, and 5 are on the same carton, I believe. Yep. So I'll just do it this way. 4, 5, 7, and 8, but not 6. Let me just say here, representations 4, 5, 7, and 8. 7 and 8 are all from the same carton and the same Levy factor, which is SL2R cross GL1R. Okay, so let's look at those and maybe see if we can understand what the difference between them is. So let's set P4 to be B bracket 4, for example. And let's set P5 to be B bracket 5. And 7. Oops, 7. And 8, just for convenience. Okay, and for example, I have the cuspidal data of P4 already, but let's give it a new name. Let's set P4 sigma 4 to be the cuspidal data of P4. And we've already seen the Levy factor of P4 is this one that I mentioned. And what's sigma? Oops, excuse me, sigma 4. Okay, so let's do the other ones. Let's do P 5 sigma 5. Oops, 5 and 7. And 8. Okay, so let's look at sigma 4, 5, 7, and 8. So what does this say? So notice that, excuse me, these two representations, sigma 4 and sigma 5, these are discrete series representations of the same Levy factor SL2 cross GL1. They have the same new parameter, 1, and they have the same lambda. And, well, this is an SL2 here. This 0 and 1 are giving you the two discrete series of this Levy factor. So, for example, I could see, let's look at the Harish-Chandra parameter of sigma 4 with, I think I want to do with respect to x of sigma 4. That's 1, 2. But if I look at the Harish-Chandra parameter of sigma 5 with respect to the same x, whoop, didn't like that. Yes, there's a little bit of, okay. This needs a little bit of cleaning up. There's an issue about not realizing that different real forms are identified. Okay, Brian, I see asked a question, which I will answer in a few minutes. Okay, so let me think for a second. How do I? So the problem here is it's a software problem, which is that the software somehow doesn't realize that these x's, x of sigma 4 and x of sigma 5, are on the same real form. So let me not try and do it that way, but let me just go back up here and say what these are the two discrete series. Well, maybe I'll say it in human terms. Sigma 4 it's the 1 on the GL1 times 2 on the SL2R. And sigma 5 is the same thing, except that you're putting the anti-holomorphic discrete series minus 2. This is the Harish-Chandra parameter. Yes, the Harish-Chandra parameter. So that's sigma 4 and sigma 5. Now, what about sigma 7? What's sigma 7? So sigma 7 and sigma 8, I should look at them both. Now, notice that, again, you have x is 0 and 1. Lambda now is 1 and nu is 2. And so what's happened is, in human terms, sigma 7 is you put the parameter 2 on the GL1 and 1 on the SL2. And sigma 8 is similarly this. Okay. Now, I'm going to plead ignorance here. When I say 1 on GL1 and 2 on GL1, the only thing I'm sure about is that that's new. I have to think about whether it's trivial or sign on the Z2 factor. So maybe I'll just make a note of that note. On the GL1, we're talking about absolute value of x to the 1 or 2, and the sign on the plus or minus 1, I'm not sure about. Okay. All right. So that gives these 4 parameters coming from this Cartan. And before I answer Brian's question and take a break for the first hour, let me look at the other Cartan. So let's look at the print block of the trivial of G again. So we've understood everything now except for 6 and its mate, I believe, 9. Okay, so let's set P6 is B bracket 6. And let's set P6, sigma 6 to be the cuspidal data of P6. And what's the Levy factor of P6? It's a disconnected split real group with Lie algebra SL2 GL1, the same as before. And as I said, from this information, you can't tell whether it's GL2 or SL2R. But the, let's set L6 to be this fellow. Excuse me. The simple roots of L6 are the short root 1 minus 1. And from that, you can tell that this is a different, well, certainly you can tell it's a different Levy factor. And with a little bit of monkeying around, you can decide that, in fact, it's GL2R. So M is equal to GL2R in this case. And, well, let's see, how could we tell that? For example, let's do print KGB of L6. It only has 2 KGB elements, and SL2 has 3. That's one way to see the difference. In any event, so now, what did I call it? Sigma 6 and sigma 9. I guess I didn't do 9 yet. But 9. Oops. Oh, I didn't define P9 is equal to B bracket 9. And now let's look at sigma 9. Well, let's look at sigma 6 again and sigma 9. Let's see, how do these differ? Well, they have different nus and different lambdas for that matter, and the same x. Well, they have to have the same x because this is GL2 and there is only one x. And so this is on the on the SL2 factor, it's two different discrete series. One of them is given by this. Well, the second one is, let's look at row of L6 is this guy here. The discrete series on the SL2 is the one with infinitesimal character rho, and this parameter here on the SL2, it's the next one up. And the news are sort of complementary. They look like this. Okay, so that gives you two parameters on this carton. And so in this block, there are four discrete series. There are four representations from the SL2 GL1 parabolic. There are two from the GL2R parabolic, and there are two from the GL1 carton. Okay, so maybe a good thing now would be to shift gears slightly and look at the block output and answer Brian's question, at least a little bit. So, there's a good reference for this, which is the algorithms paper. And well, maybe I'll write here. What these columns are the following. There's the number of the representation. There's the length. There's the types of simple roots. Maybe I'll write it this way. Length, types of simple roots. And then there are the next two columns, the number of roots. There's a column for each simple root. The next one is the cross action. The next two columns are the cross action. And then after that, the next two columns are the Cayley transforms. And then there's the parameter itself. And then finally, at the very end, there's a vol group element. Okay, so excuse me. Let's look at these things in turn. Let's start at row 0, for example. Representation number 0, its length is 0. That means it's a discrete series. Right here, excuse me. Right here, this says that the first simple root. Well, let me make a note here. A root can be imaginary, is imaginary, real, or complex, and that's denoted I, R, capital C, respectively, and that's with respect to theta sub x. So, for example, to say that a root is imaginary is to say that theta x of alpha is equal to alpha, and to say that it's real is to say that theta x is minus alpha, and to say that it's complex is neither. Neither, other, neighbor, neither, excuse me. Okay, and so this root, if you have an imaginary root, it's denoted I, and then there's the extra information that can be I1 or I2, which means that it's a non-compact root, or it could be IC, which means it's an imaginary compact root. And so these two entries here are telling you that for this representation, both simple roots are imaginary. That's because you're on the compact carton. And they're both non-compact. And that's because this is a large discrete series. All right. So these four discrete series, if you look, the first two are like that. This next discrete series, it's still a discrete series because both simple roots are imaginary. But one of them is compact and one of them is non-compact. So that's a different kind of discrete series. This is actually a holomorphic discrete series. And this guy right here is the anti-holomorphic discrete series. Okay. And then as you go down, you see that, for example, here we have a complex root denoted by capital C. And the plus means that if you apply theta x to that root, it's still a positive root. And the second root has become real. And, well, okay. So that's the information in this column. And I'll just mention that real roots, just like imaginary roots, come in three flavors: R1, R2, and Rn. And I won't say more about that at the moment. Now, these next two columns are the so-called cross-action, which is to say, if you hand me a parameter p and a simple root, you get a new parameter by applying that simple root to it. There's an action of the simple roots on the Weyl group on the parameters, and it basically moves you around on the same carton. And so these four parameters here, you see 1, 0, 1, 2, and 3. The action of the Weyl group is transitive on them, and you get all of the representations on that carton, all of the discrete series, by the cross action. Okay, and similarly, these representations 4, 7, 8, what is it? 4, 5, 7, and 8 all live on this other carton, and they're related by the cross action, as you see by looking at these two guys, and so on and so forth. This next two columns are, this one is the it shows you the Cayley transform with respect to the first root, and this column shows you the Cayley transform with respect to the second root. And what that means is the following: well, a Cayley transform is not always defined. It's defined if the root is imaginary, I1 or I2 or R1 or R2, and so this first root is imaginary, is non-compact imaginary. And what this says is that there's a way to construct a new representation from this by doing a Cayley transform, which actually takes you to a different carton, and it takes you from carton number 0, the compact carton, up to the well, the carton with parameter 6 on it. That's this one right here. And Cayley transform can be single or double valued, and in this case, it's single valued. And if you have a compact root, there is no Cayley transform, so that's what this indicates. And for example, if you go all the way down here, this I2 root has a double valued Cayley transform. And what that says is if you start with this parameter on this carton, there are two ways two formulas. Well, there's a formula with a double valued formula, which gives you two parameters on the split carton associated to it. And basically, these Cayley transforms and cross actions are operations which move you around an entire block. And it's not exactly an action on the block, but if you start with any representation in the block, by doing a series of Cayley transforms and cross actions, you can get to any other, and that requires a few extra words to make it precise because of the double valued issue. But that's what's in these two columns, and I'll say for later use that this is the heart of the Kazhdan-Lusztig algorithm. The way the Kazhdan-Lusztig algorithm, it's inductive based on these Cayley transforms and cross actions. All right, so let me just wrap up for now. This part right here is the parameter itself, x, lambda, and nu. And this very last guy here is a Weyl group element. And this tells you the action of theta. And what this element at the end says, well, in this case, E is the identity. So that says that the theta acts by the identity. And these four guys are the identity. That's the four discrete series. Right here, it says that the action of theta is, well, it's this, so there's a notation 2 hat, and there's also a notation cross. And maybe I'll just write down here what this means. 2 hat W means it's really S2 times W. Whereas 2 cross W, for example, means S2 times W times S2. It's an inverse or something, but anyway, it's conjugation by S2. So this element, let me scroll down here. This element 2 hat E is really just the Weyl group reflection S2. And that's the Cartan involution for this parameter. And and this notation hat and cross corresponds to the Cayley transforms and cross actions here. So I'll just do one example of that. If you start on this parameter number 4, and you do a cross action by the first root, you get to parameter number 7. And in terms of the Weyl group element, that's 1 cross. So we started with this Weyl group element 2 hat, and doing a cross action to the parameter on the level of the Weyl group is conjugation by 1, which is to say there's 1 cross 2. And you notice that you start at the identity, and by the time you get to the other, the split Cartan, you've got this element 1 hat 2 cross 1 hat. Let's think about that for a second. 1 hat 2 cross 1 hat E means what? Well, you start with E, and then you multiply it on the left by S1, and then you conjugate by S2, and then you multiply on the left by S1, and that's the long element of W, which is to say minus the identity. All right. All right, sorry, it's after 3. Okay, so that's a good place to take a break. And let me reiterate, this is all explained in detail here. And I should say the mathematical background is, for example, in Vogan's big green book, is a good reference for that. Okay, so let's take a 5-minute break, and according to my watch, I'll be back at 3:10.